So welcome to the Spring into STEM talk. This talk is entitled Greedy AI, Exploring an Artificial Intelligence's Insatiable Appetite for Power. So we're going to talk about some of the successes that machine learning and artificial intelligence has achieved. We're also going to look under the hood and identify some of the challenges that aren't spoken about so much. But before we get into that, we're going to start with a nice overview, a little walkthrough, some history of machine learning and its achievements. So a nice start of historical AI is that of Stanford Cart in 1979. Some very early machine learning and neural networks where this cart was able to drive around a room autonomously and get from one side to the other, avoiding chairs, which is very impressive. And it only took it something like 5 hours. So pretty impressive. That was the very early days. We can skip forward a bit to 1997 with something people may have heard about before, Deep Blue, which was developed by IBM and famously beat Garry Kasparov at chess in his very own game. We can skim forward a few more years, 2012, to Google, who reported a 74.8% accuracy with Google Brain and its ability to identify cats as well as humans. The impressive thing about this, and the reason why this was a bit of a step forward, was that when it was being trained, it used unlabeled data. So when they were training the neural network, they weren't saying this is a cat, this is a human, this is a car, but it was the neural network grouped these images purely by itself through its own training. So very impressive and a bit of a step in machine learning history. Now this next one, I don't know if it's going to frighten you or not, so take it easy. Facebook, we go with DeepFace, achieving accuracy of 97% with recognizing human faces. It's the same performance of the human in a similar situation. We keep on rolling forward through the timeline. We get to 2016 with AlphaGo. Again, we're coming back to games now, no longer chess, the game of Go. And this was developed by Google DeepMind and beat the world's leading Go player, Lee Sedol, in a very famous and highly televised match. Then Google DeepMind, only a year later it seems, took it a bit further. So originally, AlphaGo initially trained on human versus human games. It looked at these games and learned the moves from there, and then progressed on. AlphaZero takes into account no human versus human interaction with previous games, but instead either plays against itself or another agent. And so for that, it meant that AlphaZero was not flexible and it was applied to a number of games, chess, and again, Go. And then finally, we arrive at today with stuff which we've all heard about in the news, such as ChatGPT-3, generating text based on probability for the next word in a sentence within a given context. And this is already out of date. You've been watching the news recently. We've seen GPT-4 has been released, which has gone beyond text and also generating websites, generating images. So this is a nice, quick, broad overview of some of this phenomenal success that we've had with machine learning. And if we only consider this, it's a pretty phenomenal story. We've seen success and sophistication grow over the years. But the question is, how were those successes achieved? How do we actually get to that performance? And often that isn't discussed very much in public. So we're going to try and look at that now and understand some of the challenges that might be being faced behind closed doors. And we're going to go back to AlphaGo as the example. So here we're talking about AlphaGo, which was Google DeepMind's agent that was able to play the game Go. And we're looking at different variants or implementations of AlphaGo. And we're going to focus initially on this far right-hand side column, which is the ELO, which is essentially a score on how well Go is playing the game. AlphaGo is playing the game Go. So we can see if we look at the first half, scores are around 2000, low 2000s, high 2000s, which is, I think, the level of a lead Go player. But if we keep going down this table, we eventually jump from the mid to high 2000s to the 3000s. Now, this is a big step because the ELO score isn't linear, so even a small change at these high values is a significant improvement in playing ability. So the question is, how did they achieve this jump in performance? Well, to kind of answer that question, we need to look now at these two middle columns of this table. Now, what this is telling us is essentially how many computers or how much hardware is being used in that particular implementation. So CPUs are often what you have in your phones and your laptops. They do sort of general processing, and then GPUs are generally used for plotting or rendering images. As these numbers get bigger, we're looking at more sophisticated computers, more hardware, and more power being consumed. So if we consider that, go back to this ELO score, we can see the jump in score corresponds to quite a significant jump in hardware. We moved from almost 10 times the number of CPUs, and it just keeps growing essentially. So this jump in performance is partly due to this increase in the amount of hardware that we're using. And although this was the case for AlphaGo, it's also a general, it's a fact that applies to a lot of machine learning advances progression. Not only hardware, but how long we train these systems has also been increasing. So what we're looking at here on the left is lots of different sort of state-of-the-art neural networks or machine learning agents. And we're looking through time, and we're looking at essentially how long it takes to train these models. And what we see is that although we're improving performance with each of these state-of-the-arts, we're also rapidly increasing the amount of time that we're training these models for. Another point to make here is this isn't a linear scale, but actually this is an exponential scale. So this is exponentially growing. Problem with this is that as we're using more hardware and training for longer, the costs start to rack up. So on the right, we see some names we might have heard of: AlphaGo, AlphaZero, GPT. And we can again see these costs spiraling out, again on an exponential scale, so really ramping up. So we're focusing on cost here, and it seems to be a growing problem in machine learning. But there's even a more important problem, not just cost, not just the amount of hardware that we're using, but all of this is leading to very high power consumptions within the training and use of machine learning, your neural network. And so this plot gives us a nice example of that. So we're looking again at AlphaGo, and we're looking at different games that AlphaGo has played. And on the y-axis here, this is the power consumption as reported by Google Deep. So let's focus on this initial entry where AlphaGo is playing against a player called Fan. And the game, the AlphaGo is consuming around 40,000 watts. Now, is that a lot? Is it not? Well, to gauge some kind of perspective, let's consider something that will compare it against something that we know, and we might as well compare against ourselves or compare against Fan. So how much power was Fan consuming in comparison? Well, it's generally accepted that humans consume around 100 watts at rest, and equally, and their brain roughly 20%. So the Fan's brain is probably consuming roughly 20 watts. In reality, I doubt Fan's at rest. He's thinking very intensely, so he's probably consuming more power than that. But that is nothing compared to the 40,000 watts that we saw with the AlphaGo implementation. So if we compare those two agents who are playing the same game and compare the power consumption of the two, we can see there's a real discrepancy there. So yeah, so Google DeepMind, AlphaGo consuming around 40,000 watts compared to Fan, who's probably consuming 100 watts to do breathing, homeostasis, keeping himself warm, as well as his thinking, which is consuming roughly 20 watts. So clearly there's a discrepancy. How do we solve it? Well, we saw an example of how to solve this problem, again in the AlphaGo situation. So we said this first game, AlphaGo was consuming around 40,000 watts. But then when they played against Lee Sedol, it took quite a drastic cut down to 10,000 watts. The reason that change occurred was because we moved from a GPU architecture to a TPU. What is a TPU? Well, it's in the top right here. It's similar to a GPU. So it's essentially a little computer that does computing, but it's optimized for the tasks that AlphaGo specifically has to carry out. So in general, so using more TPUs and changing algorithms led to further reductions in power consumption. So it seems that one approach to reducing power consumptions in these situations is to change the hardware that we're using. We've used from CPUs, we moved from CPUs to GPUs, and now from GPUs to TPUs in Google's case. So at UCL, we're taking or investigating that very approach, but we're taking it to the extreme. We say, rather than just incrementally changing the hardware, what if we redesign it entirely? What if we take inspiration from something that we know is very efficient and try and replicate that efficiency? So we go back to our classic example of our very own brains. If we are so efficient at computing, as it seems we are, why don't we try and replicate the way we compute? So our brains are made up of neurons, and the connections between those neurons are synapses, so shown here. So if we want to start trying to replicate our own brains and physically building them, we need to be able to build or reproduce those two components, the neuron and the connections between them, the synapse. How do we do that? Well, let's first isolate the neuron and understand what that is. Essentially, a key component of a neuron is to, under some condition, to generate a spike, a voltage spike, which we can see here. So initially, the neuron produces a small voltage of minus, let's say, 50 millivolts. Then some inputs that happen, it receives some information, and if under certain conditions, it will produce a big spike and its output. Now, these spikes can be periodic. They can burst, like we're seeing here, and it's a bit like almost Morse code, where you're tapping on a Morse spike to generate a spike communication. So the first thing we need to do then is replicate how neurons communicate. So we need to replicate these spikes, and that's been done. And there's a lot of established work in that field. So what we're looking at here is an example of an artificial neuron produced using the same electronics and the same circuitry that you'd see in your phone or in your laptop. So lots of transistors and capacitors. And this circuit produces outputs or spikes at the bottom, shown with the P of the figure, and we can get periodic spikes, we can get high frequency spikes, we can even get that bursting we saw earlier. And if we can compare the output of these kinds of circuits with the spikes we see in biology, you can see we're getting quite close to it. But of course, we don't only have neurons, we also have to implement synapses.
2-minute countdown.
Cheers, thank you very much. What do synapses do? Well, essentially, they transmit information from one neuron to the other, but they attenuate it very slightly, or they might broaden the spike, for example. They can transform it in some way. The challenge in implementing synapses is that we need them to be incredibly small because there's a very high density of them. So designing them with conventional electronics is a bit of a challenge. So here at UCL, we try and replicate synapses using essentially glass that we use in the window, but on a very thin scale, 35 nanometers thin, and we break the glass by electrically stressing it. And we break the glass so that we can allow current to flow through, allow action to flow through, but we can also reverse that braking, which allows us to undo the braking and reduce the amount of that action potential that is passed through. You can see visually the kind of symmetry between synapse and the kind of device we're talking about, where we have metal, our glass, which is the insulator, and metal again. And what's nice is in these devices, you can actually replicate the learning rules that you see in biology. So we have our neurons, and we have ways of implementing synapses. Have people been able to build networks that work? Turns out, yes, there is a wide variety of research from universities as well as large companies and startups. So we can build these networks, we can build these artificial brains. Are they any good though? Let's take a look. So we have a nice example here from IBM characterizing a True North chip in tasks of image recognition and word spotting, which is essentially listening to speech and identifying a particular word. And they've got accuracies on par with state-of-the-art, as shown here, with different data sets. But the most important thing is the amount of energy that was being consumed, or power. And they were operating with a power rating of 0.025 watts, 0.275. Now, if we compare that back to our human brain of 100 watts, 20 watts, you can see we're really getting, with subhuman level there. Of course, this is doing a much more restricted problem. It's not having to move a load of limbs and also keep us alive. So it makes sense that this has less power. The key thing when we're comparing is comparing against more conventional electronics, so comparing against the CPUs and the GPUs. And there's been work that's done that as well. So with Intel, the Loihi chip, they again took their chip and applied it to word spotting. And they found that they consumed 100 times less energy in that task in comparison to GPU. So we built neuromorphic chips. There's demonstrations to suggest they do operate at lower power consumption. So if we take a step back to this timeline that we saw at the very beginning of the talk, there is that question of, will neuromorphic circuits have an impact on this timeline, and will they play a role? And it seems like that is going to be the case. Bio-inspired networks that are based on how our brains compute seem to have similar performances to neural networks, and they can achieve that at lower power consumptions. So hopefully one day we can start taking some of these points and dragging them down to have lower costs, or most importantly, lower power consumption. Fingers crossed, we'll see. So thank you very much for listening. That's the talk. If anyone has any questions, I'll keep an eye on chat and then start addressing them. So thank you very much.